Yeah, thank you for the introduction and also thank you for the invite to be here. Today I would like to talk to you a bit about lossless data center configuration in the context of consistent network updates. And before I go all into theory, first I would like to mention my co-authors. I mention all. I think the one that's here is Stefan. Oh, so he just left the room, it seems. Okay. So to start with a practical example, let's say you have a data center network, and you will not only have congestion in your data center network, but what you can also have, if it's optical link, that you can have corruption on your link, meaning that if let's say the signal arrives, then you cannot decode it, meaning you will drop the packet. And at least in one recent study, it was shown that the level of data corruption is roughly similar to the level of congestion in the network. And the bad thing about corruption is that unlike congestion, you can't really fix it with software. So you cannot, for example, reroute some flows. For example, you really have to repair the link manually.
You can reroute around the problem.
Okay, yeah, that's true. But then you will lose some capacity. Okay, you're right. Okay. Yeah. And so let's say you have one event where you want to repair a link. And since we're in some sort of toy example, let's say our routing is simple and maybe also not so optimal, that we route from U to V to D, and all these U and V send data to D. And now if you want to take this link offline, what you could do is just to change the routing to look like this on the right side, and then you don't use this link anymore. You can, for example, repair it or do something else with it. And so one simple thing you could do is to tell U and V, please change your forwarding behavior from the left to the right side. However, what could happen is that V changes its forwarding behavior before U. And then you have a forwarding loop, meaning V and U continue to send packets, the buffers will be full, you drop packets, and you will have packet loss until U finally updates. And now this is not just a theoretic problem. What was shown some years ago on some commodity data center switches that when you tell, for example, a lot of switches to update, then a lot of them will update roughly at the time you want them to update. But for some of them, it could be maybe they're under heavy load or something else that they delay their update, and then, for example, even seconds, that they straggle up to 100 times behind, meaning that this forwarding loop in extreme cases could even last for some seconds. What can we do in this case? Instead of saying both of them order update now, we could order these updates. So we could tell U, please update first, and then we have the network behavior in the middle. And then afterwards, we tell V to update, and then we are on the right side. And now what we did is we basically exchanged longer update time for not getting loops in the process. So if you basically can plan your update ahead, then you can avoid these loops. Of course, on the other hand, for example, let's say if this link just fails right now and you don't have any time to plan ahead, then you might as well also about this consistency and just tell them to update right away, because if this link is gone, you cannot send to the destination anyway until you change. Okay, and the technological driver behind these consistent updates is the idea of software-defined networking, which I will not go so much into detail here. In fact, when I took the Uber back to the hotel yesterday, even the Uber driver knew about software-defined networks. Yeah, he was a bit worried that he might lose his job at some point, but yeah. Okay, but the only idea that we basically need to take away here is that we have some central control to update the distributed switches and routers. general concept is that we have some sort of old network state, which is in some sort of chaos, or might be in some sort of chaos if we don't do something. And then we change to a new network state, and the way that we change is that we send out these updates into the network, and the switches change their behavior. And as we saw in the toy example in the beginning, there can be some problems. For example, there can be forwarding loops, or what can also happen is that you violate some firewall policies, or that you have some black holes, or that you have congestion on the way. And there are various ways to approach these consistency issues during the updates. For example, one thing would be just to try to update very fast and let the underlying protocol just handle all the problems that can happen, which is, for example, done in the B4 paper by Google in their wide area network. Another idea would be to say, let's synchronize the time really well, and let's try to really make sure that the switches update at the same time, or at least when they're supposed to update. And while this mitigates some issues, it doesn't mitigate all. There are also some problems where even if you have perfect timing, that then you still have to think about congestion during the updates. And the third approach, and this is also what I would like to talk about here, is that to schedule these updates and then to exchange some extra time for consistency. And this was, of course, I didn't come up with this. This is already done many years ago. For example, here from von Bever and others to calculate some sort of router update ordering, or to do a two-phase commit where you attach tags to all packets, for example, to say now the packets are following the old rules, then you roll out new rules to the switches, and once all the switches have acknowledged that they have the new rules, then you start tagging the packets with the new rules. And other ideas are, like mentioned down here in Swan and Dionysus, are to partially move flows around to avoid congestion during these updates. And what I would like to talk about now is two issues. One is loop freedom, one is congestion freedom, and what I would like to focus on is mainly the algorithmic ideas here. So let's start with loop freedom. And as we saw in this toy example earlier, what we could do there is sort of to compute a router ordering to say, first you should update and then we should update. And if you just have rules that work for a single destination, then you can always do this. Because when you look at the new routing rules, they form a tree. And then what you can do is you update the children of the destination. And since you just point at the destination, you can't have any loops. Then you go to the next level of the tree, the next level of the tree, and so on and so on. Meaning you can always update like this. But the bad thing is that this can be slow. For example, if the new tree is just a long line, then you need a linear number of updates to do so. So the natural question that comes up is, can we be faster than this? So maybe we can update tree level 3, 7, and 10 at the same time without having any loops. And sort of a sad answer to this is that already figuring out if you can do it in sort of 3 updates, one after another, is NP hard. So what can we do if we can't compute an optimal algorithm? Maybe then let's try just to be greedy. Let's say we take the current network state and we just try to update as many switches as we can, and then we just go on and on and on until we're done. And the good thing is that, at least in this way, we won't run into any dead ends, meaning that even if we perform this in a greedy way, we will eventually reach the new routing rules without having any loops. But there's again a downside and an upside. Again, if you want to maximize the number of switches you can update right now, this is again an NP complete problem, because it's very closely related to the feedback arc set and the maximum acyclic subgraph problem, which essentially ask, if you have a graph, like what sort of edges do you need to remove all cycles, or like how many edges can you include without having cycles. But on the other hand, since these are well-studied problems, we can also use their algorithms to get good approximation ratios for this greedy update method. However, if you still do this like greedy step by step, the bad thing is that there are instances where you could be done after a constant number of steps, but if you do it in the greedy way, you might basically run into a linear update schedule, because since every time you update, you sort of change the topology of this routing tree a bit, and then you can sort of need to solve some dependencies that will take a long time. So what can we do, since we can't find an optimal one, and since this greedy one can destroy good instances? And there's one idea that Stefan had some years ago, and that was just to relax this problem. And there are two key ideas here. And the first one, instead of saying we route just to a destination, that we look at source-destination pairs and look at routing rules for those. And the second idea is that instead of saying we don't want any loops in the network, that since now we route a source-destination pair, that we don't want any loops on the current route between the source and the destination, meaning that if there's a loop somewhere else, but it doesn't get fed new data from the source, we don't care so much. And to give you an idea why this can be better, let's look at this network. Again, it's a bit artificial, where the old routing rules just go from the left to the right, drawn in solid, and the new ones go in dots, so they go here, then they go back and back and back and back, and then to the destination again. And now if you want to update this in a non-relaxed manner, then the problem is, for example, let's say you want to update this node to no longer route here, but to route back here. That then, in order to avoid a loop, you first need to update this one, but then to update this one, you need to update the next one, the next one, the next one, and so on. Meaning you need a linear number of updates. But if we now relax, we could do the following. We first just update this forwarding rule. And if we now look at where does the traffic go from S, except for the packets that are still in flight, the traffic just goes like this. Meaning that now we can update all these nodes down here, all at once. And then all what is left to do in the last step is to tell this node, please update to here, and we're done. And so the idea here is what they call is a peacock algorithm, based on the idea that you try to skip a lot of the nodes that you want to update. And then sort of like a peacock that spreads its feathers out, you don't really care about what's going on below here. So you can update this all at once. And with this idea, you can always cover a constant fraction of the path that needs to be updated, meaning you're done after a logarithmic number of rounds.
But if you go back and say, okay, if this short path is okay, why don't you stay with this short path? It's a much better path than, you know.
Yeah, it's true. I mean, you mean why you initially didn't choose this path already?
If it's okay with congestion, you can do this short path, you know, and then the rest of them are out of traffic, and you can do whatever. Then you might as well keep the shortest path.
Yeah, it's true. So this is then just more like a small example to show a case where, like with this relaxed case, you can be very fast in 3 steps, and the other one takes a linear number of steps. So it's true. So a more realistic example, the gap might not be so big. It's true. And so is this peacock algorithm actually optimal? And at least the analysis of this algorithm is optimal in the sense that there are instances where this peacock algorithm needs a logarithmic number of updates. But in practice, it's not so clear because maybe you can do something else except for this Peacock algorithm where you cover long distances, then update below and go on and on. And in fact, you can write like an integer program that tries to find the optimal solutions to any instances, and the best and the worst instance that's right now known with over 1,000 nodes just needs 7 updates. So it seems that at least in practice you can be done very fast, even though the lower bound for this algorithm is log n. And previously I said a bit, okay, like this greedy algorithm can be like very bad in theory, but when you look at it in practice, and here we took some autonomous systems, we picked some destination, we took some shortest path routing with link weights, and then what we did, we just like took one link out and said, now compute the new shortest path routing. How long do we need to migrate to this new shortest path routing if we just do it in a greedy way? And we run this a few times and then plot it here for the individual nodes, like for how many updates do they need to wait until they can update. And as it turned out, like most of the nodes, like some of them don't even need to update. Some can be done in the first round, some can be done in the second. And so like a very large portion of the network basically doesn't need to wait so much. So it's also quite fast in practice. So now we went a bit down, like from this original tree idea to this greedy idea to this relaxed idea, and now back. And since we're going back, let's also go back to the tree idea again. And one downside that we didn't discuss yet so much is that in these consistent updates, what we do is we take the controller, we send out updates, the switches implement them, they acknowledge them, the controller sends out new update back and forth and back and forth. So wouldn't it be nice if we didn't need to do that? If we could just fire and forget, we throw the updates into the network and the network sort of handles it on its own. And what you can do here is to sort of use some dualism to so-called proof labeling schemes, because you can think of the centralized controller as some sort of prover that knows, at least hopefully, what's going on in the network, and can then send out proofs to the individual nodes in the network. And then if you add some intelligence to the switches, they can look at this proof and then sort of decide when can I update in a safe manner without any further interaction to the controller. And to give you some idea about this, so let's say that you're a switch and you ask yourself, when can I update without introducing any loop? And this loop could be, maybe it's 100 hops long, so you have no idea how to check it locally. Well, all you really need to do is to know, if you do this tree ordering idea, that you just need to know, like, who's my parent, and when my parent updates, I can update as well without introducing any loops. So if you have this information, you can just wait for your parent to send you the information, like, I'm your parent, I update it, and then you can update too, and basically don't need any further switch controller interaction. And you can also extend this scheme a bit in the sense that you can also push out new route updates even if the old one is not done, and you won't introduce any loops. And similarly, by also encoding in how far is the destination away, you can also check if the controller sends out bad updates, in the sense that if you would update to them, that you would introduce loops, but then the nodes could locally detect them and tell back to the controller something bad is going on, I'm not going to update, to not introduce any loops. But the downside, of course, to this is that you now require some sort of intelligence in the switches, that they now sort of need to maybe communicate with the other switch, like tell them, hey, I'm this switch, I updated, now you can update as well. And but now, for example, at SOSR this year, there was a paper that had the idea of putting like a small controller on every switch to sort of handle these issues. Yeah?
You may have mentioned it, but the tree ordering requires some pre-processing, right, before you do these updates. So what is the overhead for this?
Yeah, so the overhead would be that that the controller computes this update. And so the switches can't do it on their own unless we sort of go into some sort of distributed system that does some distributed computing. So the overhead would be that the centralized controller needs to sort of obtain the state of the network and then push out to the switches just who's their new parent in the new routing. And then the individual node then basically waits until this parent says, hey, I updated, and then they can update too. Okay, so much about the loops. Okay, 10 minutes, thank you. Okay, now I would quickly like to go into congestion, because in this previously loop updates we didn't look at congestion at all. Maybe if we updated in some fashion we would have a lot of packet loss due to congestion. And the way that's all roughly currently the state of the art for these congestion-free updates is that we use this packet tagging approach about which I talked earlier. So that when we have the flows in the network and all the flows have some tags, like I'm flow 7, I'm flow 8, that when we push out a new update, we install new flow routes in the network and then tell the sources, for example, now change from the flow tag from 7 to 7 prime, and that then the routes, then the flows get routed along the new routes. If you want to do it without this flow tagging, the only work that I'm aware of is something by Stefan on Arxif right now, where he looks a bit about congestion-free rerouting on directed acyclic graphs. But I'm not going into detail about his paper now. And I would rather look at the currently known algorithmic ideas. So this consistent migration of flows, it was formally introduced some years ago at SIGCOMM, with the idea that if you have a flow, it can be on the old route or it can be on the new route, depending on when it's getting updated. So if you push out an update, what you want to ensure is that for every edge, no matter if the flow is on the old or on the new route, you don't violate the capacities. And for unsplittable flows, sort of similar to like unsplittable flow optimization without any network updates, this is NP-hard. And the algorithms out there are basically integer programs that try to figure out how to move these flows around. However, similar when you look at basically splittable flow optimization, it gets easy again. So what about splittable flow optimization if you want to migrate without creating any congestion? And for that, I would quickly like also to give you some example. Let's say you have two flows, a green one and a blue one, and they have a capacity of size of 2/3, and all the edge capacities are 1. Now, if you would update them at the same time, it could be that blue moves before green, and then you have some congestion on this edge up here. And in fact, there's no ordering for this update to happen, because no matter which one you move first, you will have some congestion on some link. But what you can exploit is that you have some free capacity on these links. For example, on all these links, we have a capacity that's free of at least 1/3. So what you can then do is you just move like this 1/3 of the flow of the flow size at once. So in this case, we split the flows into 2, and we move half of them into the new paths. So that after this update, they're split into 2. And then, since this invariant still holds, that afterwards we still have free capacity of 1/3, we can then do the last step, and we are done. And this idea basically only works if you have some free capacity. So maybe you're lucky and you have free capacity, or you can turn off some sort of background data. But what happens if you don't have free capacity on where you want to push around the flows? Well, okay. I mean, if there's no free capacity at all, also nowhere else, then you sort of have to decide, do I just accept this temporary congestion, or do I maybe rate limit the flows? So in the worst case, I just have to do it. But what happens if you have some sort of free capacity somewhere else? Because then it's sort of a bit like, in this case, like variable swapping. You could just move one flow somewhere else, then you move the other one, and you're sort of done. And conceptually, it's a bit similar to the 15 puzzle you probably know, where you sort of have to move these numbers around in the end, get an arrangement that's from 1 to 15. And if you solve this with sort of like a brute force approach, you might have exponentially many possibilities how these numbers could be on this board. But in practice, you can solve it in polynomial time. And it's also the same case for splittable flows. Because the fundamental idea is that if you want to move a flow somewhere and you want to be safe from temporary congestion, you want to have some free capacity somewhere. And if you have free capacity everywhere, then you can just move step by step by step. So let's see, with what sort of idea can we create free capacity? And instead of going like by linear programs or integer programs, what we're going to do is we're going to take a combinatorial approach, mainly using augmenting paths. So let's take this network where we have a flow sizes, like the flow size of 1 on each of the two paths, and we have capacity of 1 as well on all the links. And let's say that now we want to create some free capacity on this link by moving the flow a bit around. We can now look at the residual network, meaning we first look at where can we actually increase some flow sizes. And that's on the edges here when there's nothing. And where could we remove some flow sizes? And that would be on the edges where there is already some flow. Meaning that now if we combine these two ideas, we have the resulting residual network. And now in this residual network, we can search, for example, if we want to create some free capacity on this edge, is there some path from U to V? And in this case it is. We just go up here. And then this allows us to create some free capacity on the link. And now what we can just do is, since we need free capacity, for example, to move some flow somewhere, we just try to see in the final and also in the initial state, can we create free capacity on the links with this idea of augmenting flows? And if we can do that for all the flow edges in the old state and in the new state, then we can just migrate step by step by step and are done. And what you can also show is if there's some edge where you want to, for example, remove some flow, or where you want to put some flow on by just moving these flows, and that you cannot create free capacity with this augmenting paths idea, that then you can also not migrate in a consistent fashion. And if you now use this idea in sort of like a brute force approach, just try to create augmenting paths everywhere, and when you create some free capacity, you try again and again and again. You get like a bit bad runtime, but still polynomial, like flows times edges cubed. I mean, you can improve this a bit.
So it's not depend on the total slackness? If the slackness is very small, it's 1 over epsilon, it must be dependent on the slackness.
Yes, that's true. Like the migration time is dependent on the slack, but the decision time to find out...
decision whether there is a... Okay.
Yes, that's true. Thank you. Okay, 1 minute. Okay, so then let me wrap up. So now I presented you some algorithmic ideas for consistent updates in networks, and what we looked at was for the loop freedom ideas to just do it in a greedy way, or to do it in this relaxed way, or to use these proof labeling ideas where you throw the updates out into the network and don't care. And lastly, for this consistent flow migration, the approaches that are out there is firstly that you do some integer or linear programs, where, by the way, it's not clear if you can now decide it in polynomial runtime or not. There are now algorithms out there that if you have this consistent flow migration and you want to decide is it possible yes or no, that do it in polynomial runtime with the integer or linear programs. But if you want to decide in polynomial time, at least for splittable flows, you can do it with this idea of augmenting flows. And with that, I would like to conclude, and thank you.
Thank you.